Hello, and welcome to today's presentation, How to Choose the Right PVD Coating for Your Product. Thank you for taking the time to join me and my colleague, Augusto Kunrath, who's the R&D manager here at VaporTech. In the webinar, Augusto will discuss the different types of PVD coatings available, their characteristics, and which are best suited for specific applications. The webinar includes a presentation and a Q&A session. If you have questions during the presentation, please enter them by clicking the Q&A button on the Zoom ribbon and typing them in, and Augusto will answer them at the end. Now I'll turn this webinar over to your presenter. Augusto has more than 25 years of R&D experience working on coatings and surface engineering solutions. He has degrees in mechanical engineering and material sciences and numerous technical publications in peer-reviewed journals. Augusto?
Good day. Yeah, thanks, Lucy. So I'm going to take it from here. Good day to everyone. We're going to be talking about different coatings, how you select those coatings, and some examples of applications. You see during the process, I'm going to talk about some different things. As you know, you're going to have quite a few minutes at the end of the presentation to ask questions. So let's get to it. So why coatings? And a lot of times people think of that after they have a certain application. They have either tool components or something that you can and want to improve the performance of. And it comes after you already have completely developed either the component, the tool, or the part that you have. And that's okay. It's not that it's a failed process of developing, but there's other ways to do that as well, in which you have use the coating as part of your design element, or the way you design your component, your tool, or your part, right? Another question that sometimes comes up is why coatings? Why wouldn't you just make the entire part that you have out of that material that you have in the coating? And there are four good reasons why you don't do that. First of all, you may not have the availability of that material being in bulk to actually make it. Cost could be prohibitive. Fabrication limitations. Most of these coatings, especially in performance for mechanical applications, they are quite hard. So how would you manufacture these parts? And of course, there's application requirements. The fact that you have a material that goes on the surface of a part doesn't necessarily mean that that is the best material. You have to think of material in the substrate, meaning substrate being the tool, the component, as a team, right? So the properties of both of them will affect how your component works. In terms of the coating selection process, I want to, before we even talk about what's on the screen, I want everyone to look at the application that they have and understand exactly what problem they are trying to solve, or what opportunity you're trying to advance, right? There's commercial reasons why you do something, but there's we're going to focus here on the technical reason, right? Why you want to go with a coating. So first, look at your application, make sure that you know what hurts, right? What's preventing you or preventing your parts or components, your tools from performing better and achieving what you want to achieve in terms of production or performance. Okay, so things that affect the coating selection process. One, of course, is the most obvious, is the environment. If you have a mechanical application, that meaning you have a wear of your tool, be it abrasive wear, adhesive wear. You can have tribal oxidation, you can have impact, right? So you have a situation where something is producing a fatigue environment where your part or tool is failing. You can have chemical situations in which your part is exposed to an acid solution or a base solution or high temperatures or so forth. You have situations where your component has to work in an environment where there's either a bio, how can I put this, biological contact, be it because it's something that goes into the body, or in medical applications, some tools that you use, and so on, and also temperature, right? So if it's a high temperature application, you have to make sure that not only your coating, but your substrate that can operate in those conditions. Then there's function. Sometimes all you want from the coating is have a cosmetic appearance that is appealing to whoever your customer is. There are situations where you're basically and only concerned about performance. It doesn't matter what their part is going to look like. It's just as long as it performs, because it's not visible to whoever the user is. And there's many situations where you have a combination of both, right? So it has to be cosmetic appealing, but at the same time has to withstand certain conditions of the environment, be it any of the ones above. I put here substrate, even though it doesn't seem that the substrate would matter for the coating that you're doing, but things that do matter is the composition of that substrate. So adhesion of your coating to that substrate is obviously important for any applications that you may have. Mechanical properties. So if you have a substrate that, or an application where you have impact, you have abrasion, you want both of your team, in the case the coating and the substrate, to be able to sustain that kind of abuse, be it, like I said, mechanical one, and temperature limitations as well. So melting point, glass transition temperature of the part, and heat treatment that that part suffered. In the case of what we're talking about here in melting point, glass transition temperature, and heat treatment is not necessarily about the coating, but the process that you use to apply that coating. So for example, if you have a material that is heat treated with a tempering temperature of, let's say, 150 degrees C, during the process that you use to deposit the coating that you want, you may need to exceed that temperature. So obviously that coating or that process that is needed for that particular coating is not ideal, right? So you have to work with that regard as well. Another thing that's important is, let's say you have a material that can withstand up to 400 degrees C, and you apply a coating that can operate up to 600 degrees C. The fact that you put that coating with a higher temperature, resistance, it doesn't mean that the entire component can be brought to that situation, right? You're still limited by the temperature that your substrate can withstand. And I have some of that, some of considerations like that in the blog that is listed here at the bottom. I'm sure you're going to have access to the presentation itself. You can always click in there and read a little bit more. It's a quick read, so it's nothing too much depth. Following that, there's always questions that can be asked to us. Okay, PVD functionality. So where exactly is the functionality of a coating, right? So there are some situations or some of the properties that you want from that coating that are immediately at the very surface of the coating itself, such as lubricity, for instance. Excuse me. Hydrophobic properties. That's something that's really at the very surface of the coating itself. Reactivity, corrosion, oxidation resistance, and so on forth. But there's also stuff that is in the bulk of the coating. So color, hardness, toughness. Those are properties or characteristics of the coating that are mostly in the bulk of the coating itself, right? Not necessarily at the very surface. And how is that functionality achieved? So you can achieve that by choosing the composition of that coating, and that goes all the way from a pure metal. There's many applications that is just a metal that you apply on top of your substrate part, but also can be, carbon-based, such as diamond-like carbon, could be nitrides, carbides, oxides, and combinations of those. So this is purely the composition itself, but in combination with that, you have to think about the morphology of that coating. So how dense that coating is, the structure, how it grows on top of the substrate, right? And the third is the architecture. And what I mean by that, you can have a coating that's a single layer, meaning a single composition, or you can have an architecture where you have multi-layers, meaning, stacks of different layers, one on top of the other. You can have graded layers where the composition changes from where it contacts the substrate all the way to the surface. And you can have nanostructured structures in which you have small particles, let's put it that way. And I'm talking about nano size, nanometer size, in which those particles are inside the coating. So all of those aspects do contribute to the functionality of the coating. And we have here just a couple of examples. We go all the way from optical coatings to hard coatings using tools, photovoltaics, which are properties of coatings have to be such that you have a certain response. Optoelectronic properties is the term for that. How do we apply these coatings? And the only reason I'm talking about this is it helps understand where it comes from, right? We are talking about PVD, and I'm going to talk about PECVD as well to some extent. PVD stands for physical vapor deposition. So the coatings that we're talking about today, in general, are created by one of these three processes in here. So the two on the right-hand side, cathodic arc and magnetron sputtering, these are PVD type processes, physical vapor deposition. And what that means is that most of the material or part of the material that you're depositing on your part comes from a solid source, right? On the other hand, PECVD, or plasma-enhanced chemical vapor deposition, is a process where the material that's being created on top of your part comes from a precursor that is either a gas or a liquid. So there's different processes to create these thin films or coatings that we're going to be talking about today. In terms of materials, and this is mostly for PVD, physical vapor deposition, we have, these are the typical metals that we use either for cosmetic or decorative applications, as well as performance coatings. We will see that although some of these coatings can be used for decorative applications, most of them, the ones we're going to be talking about today, do have properties or have properties that can make them useful for applications in tools or mechanical components. In terms of gases, so during the process that we're talking about here just a minute ago, we have PVD and PECVD. So you have, in the case of the PVD, you have those metals that we're talking about, zirconium, titanium, chromium, tungsten, aluminum, and so on and so forth. But along with those, to create the nitrides, the carbides, oxycarbides, we use a series of gases, right? Which are, generally speaking, nitrogen, oxygen, and there are two different types of sources of carbon that we can put in the coating. Methane and acetylene are most common ones. In terms of PECVD, then generally we would use acetylene with an adhesion layer that's a metal, but we can use also a PECVD type adhesion layer that's created with a specialty type of gas. So you can see that most of these metals are clustered in a certain area of periodic table, and same thing for the gases. So this is pretty typical, and you're not going to see much of a variation of these materials throughout the industry. So let's talk about the coatings now, and this is something that put together just because since you're going to have the presentation, you can go back and look at this. What this is, and it doesn't matter who you're looking at in terms of companies and people that produce coatings, right? Everybody likes to have a certain number of coatings or types of coatings that are used for certain types of industry or certain applications. Reality is that each case is slightly different. We do have some general rules, right? But that doesn't mean that your application, if you're gonna either venture into using coatings or you are someone that uses coatings, that is completely tailored for your application. You really have to see the environment. For instance, if you have some sort of machining operation, turning or milling or so, it's not just the operation itself, it's what your substrate is, meaning the tool, what type of lubricant or refrigerant or cooling medium you use, and what type of material you are machining. So all of those may come into play when you're trying to decide what kind of coating you're going to be using. Right? But in terms of market, you have consumer products. A lot of consumer products that we use on a daily basis do have coatings. So the faucets that you have at home, even if they look, some of them just have a chrome plating on top, but many of them that has slightly different color, you will have most likely a PVD coating on top. Sometimes that can be an organic type of coating, but in many cases, if it has a metallic look, it's going to be a PVD coating. Automotive, you have all sorts of applications, all the way from cosmetic, goes into exhaust pipes to speaker covers, but also very specific mechanical or performance applications, such as engine components, transmissions, and so on. In the medical field, you have implants and surgical instruments, two different applications, put it that way. One thing has to have, or both of them have to be biocompatible in the sense that they do not harm the tissues, whatever they're going to be in contact with. But in the case of implants, you're really not too concerned about the cosmetic appearance of what they look like. In surgical instruments, it does come into play because you can use these different PVD colors, for instance, for a quick assessment of the surgeon to choose the right, or the assistant to choose the right tool, even though they sometimes look exactly the same. It's just a question of different sizes, but choose the right tool for the specific operation that they're doing. As well, it's something we don't think much about. You don't want those instruments to have to be reflective, right? So they have very intense lights when they're operating. They want that things shining back into your eyes while you're trying to accomplish a given task. In the energy sector, you have oil and gas components, renewables. That's not something we delve much into it. In terms of the renewables, of course, oil and gas components, yes, there's a very large application of the types of coatings that we do, for instance. And of course, manufacturing fabrication, we talked about that. It goes all the way from machining, die cast, injection molding, punches, or stamping, and so on and so forth. And on the right-hand side, you have some of those typical coatings that are used. Do not get too attached to that. Always think that for each application, you may want to be more specific about how you choose that coating. In terms of decorative, and whenever we talk about a PVD coating or a PECVD coating that it has a decorative application, you have to think that durable as well. This is not paint, right? This is a process that applies a hard coating to the surface of your part that is very durable, very high hardness, very good adhesion, and it's going to last a lot longer than if you just paint that part. And some of the consumer products that are typical that use PVD and PECVD DLC, plumbing industry, meaning faucets, door hardware, automotive, cosmetic, and I specifically put cosmetic in here because there's some parts that is just for the color. There's durability applied to it, but it's mostly you have to have a certain color in there. Sporting goods, and jewelry. One would think that it's not just fake jewelry. Some manufacturers, some people that work with jewelry, sometimes they use coatings like this to either increase the life of the appearance that you have, or just give you some more durability, or change the color as well. In terms of these decorative coatings, that I call it types, but what we're going to talk about here is that how that coating creates that color, creates that appearance, right? So in terms of, we like to call what opaque coatings, and those are coatings in which the color is independent of the thickness of the coating that you put in there. So there's no optical tricks to create that color. Once you put the coating on the top and it's over a certain thickness, it will maintain that color independent of anything else. So those can be, even less, about 0.1 micron, but typically what we do is normally 0.25 to half a micron. And it works really well, even in very complex geometries for the process that we use. And it's a majority of the common decorative coatings. We do have other types of coatings as well that use optics to create that particular color. So it's a semi-transparent coatings. Normally they are multi-layers, right? And at the end of those multi-layers that are controlled in terms of thickness, you can achieve a certain color, a certain luster. And most of them are either metal oxides or they are diamond-like carbon. One would think diamond-like carbon is only at that gray color. Diamond-like carbon normally has a semi-transparent appearance, and only after a certain thickness you start seeing an opaque color. That's why it's listed here. Just to give an example of the range of decorative application of decorative colors that you can have, even with just a single element, which in this case is zirconium, right? Or the metal element of the coating. All of these are colors that we can create with a single type of target, single type of metal that you start with, right? It's just a question of applying the right amount of the gases and the parameters during the process, but all is done in the same very system with the same target being the metal source that you use to create the coatings. The only example that I have that's different here is chromium, and this is just our palette here that we use at VaporTech when we are creating decorative coatings. For performance coatings, then most of what we're talking about here, we're going to put aside situations such as optical coatings or optoelectronic coatings or electronic coatings. That's a completely different category. We're talking about most, in this case here, what we normally offer coatings for tools and mechanical components. Those goes all from cutting tools, anything that's used in machining, to punches, plastic injection mold, die casting, surgical instruments, including cutting, as well as those that you may use during surgery. Mechanical components, the ones that are more easily identifiable are automotive engine components, but as well transmission, and so we'll use coatings and bearings, right? Whenever you have friction due to sliding of two components to each other, if you can apply a coating in there that is either has a low friction coefficient or has high hardness or have both, you're gaining on the performance of that particular component. Now, talking about some specifics, or talking about some of this coatings, some of these materials that we are discussing here. Let's talk about zirconium nitride, in this case, decorative or durable decorative coating. Has a metallic aspect or appearance. It can go all the way from neutral to yellow to brass. Process that we normally use for that is an arc deposition process. And is a scratch resistant, gouge resistant, and has excellent corrosion resistance. That's a good point about zirconium. All the zirconium based coatings have really high corrosion resistance. But and you can see here examples of of the same material, zirconium nitride. The way you create that is during the process. If you have a smaller amount of nitrogen in there, you come close to a nickel color. I know that many of us, we look at these things, they all look like chrome, but nickel has more of a yellow tinge to it, while chrome is more of a bluish color. It's still with that metallic look. If you put more nitrogen into it, you can actually create a brass-like color. So that's all you can achieve with the very same material. And interestingly enough, you can use the same material in a performance application in which you have, you're not too concerned about the color, even though it may be used an indicative of what the coating itself is, but really you're looking at the properties of that. Zirconium nitride is used extensively in implants, be it dental or as well, prosthesis. It has extremely high corrosion resistance, very, very good wear resistance. The hardness of this thing is about 2,500 Vickers, 25 gigapascals. So it's an extremely hard coating. It has this color if you have it fully reacted with nitrogen. And there's many applications besides biocompatibility. If you use the same process, but you add now either methane or acetylene to the process itself, you can create a decorative coating that has a different color, right? You're still going to have a metallic appearance, but now you're going farther into the color range, and you can get, like we have more of a light bronze color. You can create a gold color, a very saturated gold color, or you can create a rose gold color. All of these are standard processes that we have, maybe some other companies have as well. It's just a question of changing the process itself in terms of what kind of gases you're using and what kind of electric parameters you have in your vacuum chamber. But you have a very high flexibility of changing color just by adjusting parameters of the process. That's all done with the same type of system, same type of target material, which in this case, again, is zirconium. One other, just to give an example of another type of coating that you can produce with zirconium, is instead of nitrogen and carbon, but if you have oxygen and carbon in your film, you can create different types of colors. These are all manufactured, they're all what we call Xerox, and they all have, again, a metallic look and can go all the way from light gray to black. The way you do this is not by changing the amount of gas that you have during a single process to create these colors. You have different layers, multi-layers, in which you have different indexes of refraction as you build that coating, and so you trick the light, or you trick the eye with how the light reflects off the surface of the part. But these are all decorative coatings as well. You have something that's more on the performance side. A key, again, here, this is a situation where you're interested in having a component, a part, a tool that is visually appealing, that you have an interesting color, but it does have to perform for the test that's designed for. So in the case, just a blade. So you can apply Xerox to blades. It does have a high hardness. It's not as hard as zirconium nitride, for instance, but it does have more than enough hardness, or much higher hardness than the substrate itself, independent of what type of metal you're using. This coating is going to be harder than that. In our case, it's produced with cathodic arc, and you can obtain all those colors from a graphite or gray color to black. Changing materials now. We're all talking about just PVD so far, right? So with PVD, you have a metallic source, a solid source from which you create your coating in combination with different gases. So titanium nitride is probably the most common, maybe. Nowadays, it's difficult to say, but it's the oldest performance coating and decorative coating that has been used since the 70s. right? So it does have very high hardness as well, which is a common theme for all the coatings that we're talking about. Very good thermal threshold, 500 degrees C, which is pretty much about the limit that you're going to find some of these tool steels that are available. And again, the way we gauge that for a steel or a substrate is what's the tempering temperature. For those that have a little bit more understanding of metallurgy, a steel can, if it is heat treatable steel, it goes, you heat it up, you quench it down, and then you heat it up slowly again to a certain level to have the right combination of hardness and toughness of that particular metal or steel, right? So that temperature, that's called the tempering temperature, is what defines not only the temperature that this thing can operate, but the temperature to which you can take it during the deposition of the PVD process, right? Again, this can be done with cathodic arc or can be done with sputtering. It's a biocompatible material as well. Cosmetic appealing, very hard, resistant to abrasion and adhesive wear. Has this very typical color, gold. It can vary a little bit paler, a little bit darker, depending on the amount of nitrogen that you have in the coating. And here's some of the applications, which I'm going to summarize at the end with a table moving forward. If you do the same way we did with zirconium, if you add now some carbon to that coating, you generate a different type of coating that's not only different in terms of the color that you have, but some of the properties are different. And it's interestingly enough, this is a harder coating. The thermal threshold is a little bit lower, but it's harder, and as such, it's used in some applications that you have a need for wear resistance. It tends to change color anyway from rose gold to gray. Most cases, really not an issue, or not something you look for. It's just general information, and can be used in machining operations where you have high pressure. For instance, tapping. Tapping is the operation where we create threads, and it's a slow operation most of the time, and it creates a lot of pressure on the teeth of the tool. So this is the one of the type of codes that works in that particular application. Plastic processing as well is another one. Chrome nitride. Chrome nitride, of all these coatings, again, staying with the theme, this is PVD. You have now chrome being your metal, and nitrogen is something that you add to it. Of these coatings that we're talking about, this is the one with the lowest hardness, but it has a very high toughness. And toughness in materials, it is actually a technical term. And what it means is that when you do have impact, or you have a situation, be it fatigue or something else, that creates a small crack, for instance, a tough material is the material that prevents the propagation of that crack that would lead to a catastrophic failure. So applications in which you have impact, that you have thermal shock or something along those lines, chrome nitride is in general one of the best possible coatings for those types of applications. You have a higher threshold, thermal threshold at around 1000 C, reasonably good coefficient of friction, can be produced by arc or sputtering, and on top of the excellent toughness that I was talking about, it can also withstand environments where you have some oxidation. So it has a high oxidation resistance. Application include all the way from metal forming, plastic molding, engine components, intake and exhaust valves. We have an example here. Changing gears a little bit, we were talking about PVD, physical vapor deposition, and to create a coating such as diamond-like carbon, we use a different process, which is, like I mentioned before, PECVD, which stands for Plasma Enhanced Chemical Vapor Deposition. It can be done in the same systems that we sell. So you can do PVD and PECVD. And the main product that we do with that is the so-called DLC. Now, DLC is a term that's is used very liberally. There's many different types of coatings that fall into that general category. The most common one is the hydrogenated amorphous carbon, which is the one here, A-C H. And that's the simplest one. Is basically the composition of the coating is carbon, right, with some hydrogen incorporated to it. You have other types that incorporate metals. Typical metals are chrome and tungsten. You have possibility to incorporate non-metals, so silicon being one of them. And you have situations where you can create a coating that doesn't have any hydrogen. You see all the other ones that I talked about, they have some hydrogen in them. And the reason you have the hydrogen in there is because DOC is something that sits between graphite and diamond. Both are made of exclusively of carbon, right? And DLC is something that sits in the middle. So what you want to do with DLC is to create something that has some of the structure of the diamond, but retain some of those properties of the graphite as well, such as lubricity, low friction, and so on. So that's what I represent here on the top. Basically, what it's trying to do is have a combination of the two types of bondings that happen in graphite and diamond. So sp3 is what is associated with diamond. sp2 is associated with graphite. And we're not going to go into detail. There's a lot of very cool physics that goes into that. But for the purpose of our discussion here, the more sp3 you have, the harder the coating, the more sp2 you have. Now you migrate more towards what a graphitic material would be. All of those are very hard. This is for materials that do have hydrogen incorporated, such as the hydrogenated amorphous carbon. You have anything between 1,500 and 2,300 Vickers. We normally present that in terms of gigapascal as shown in here. Very, very low coefficient of friction. So pretty obvious that many of the applications we have are contact applications where you have some sliding contact. But we also can use diamond-like carbon as purely as a decorative coating, as you can see on the bottom here, the picture on the bottom, that you can achieve this coloration between gray and black. And to finalize the different types of coatings, just to go a little bit off what we were talking about, we do have a development into antimicrobial coatings. EPA, which is the agency that monitors and controls anything that is sold in this, but they're very strict about how you talk about this. And we are still in the stage of registration with them. We have a pending EPA registration currently on coatings that we produce or in-house, so we're developing in-house that contain copper. Just as general information, copper and silver. Two of the elements that do have this pesticide type or antimicrobial characteristic. So if you have a good way of incorporating those, you do have an opportunity to create an antimicrobial coating, right? Again, there's lots of hurdles you have to go through to create something that's durable. But on top of that, you do have to comply with many different rules and regulations that the EPA put forward. If you have any questions, you can contact us at vtsales@vaportech.com, and we can go into a little bit more detail. So summarizing, you have all these categories here that we talked about before, and I have, again, some of those lined up on the right-hand side on what normally is used for those different applications. Bear in mind that you can always, or you should always pursue something that really addresses your need. If you're going to go to the extent of putting a coating on your part or tool to improve its life or just the quality of what you're trying to produce, you have to think hard about everything that goes into it. Right? It's not just, don't use just a canned product. We can guide you through something like that if it comes to it, but contact us and we can guide you through the process. Just to give an idea what these machines look like, they're all vacuum machines. different sizes. So you have machines that do cathodic arc and PECVD, machines that can do everything, all the way from cathodic arc to sputtering to PECVD process. And you have all the machines that have more specific use. They're for extreme high performance mechanical components and so on. So you have an array of different machines that you can use to accomplish the coatings that we were talking about. I believe we're getting to the end of the presentation. Yeah, quarter to the hour. So we're going to turn to Q&A. Jose, is there anything you want to talk about before I go into the questions? Looks like we lost Jose. So I'm going to jump into the questions here myself. I have a question of what's the maximum size of components that can be PVD coated if possible. Okay, that basically depends on the size of the machine, right? I can't speak of what other companies do. We have, if you go back here, this machine here, just to give it a size, a person up to 6 feet tall can fit inside the chamber. So we are talking about 48 inches in length. The overall envelope of the part then depends on what system we're using again, but in general, a diameter of 8.5 to 9 inches plus the number of parts that you can put in there we could deposit using that particular machine that I just showed. Gases used in PVD coating will be generated by your system, or they have to, yeah, no system that I know of can generate the gases that you use. We have our system are more industrial based, not as much in the semiconductor industry. So we don't need 99.999% gases. Normally industrial quality gases is good enough, but it does come from an external source. You have to buy cylinders from a local source. We don't provide the cylinders. Have parts at about, that's another question, sorry. 300 by 300 by 300 millimeters to 1.8 meters. Yeah, those parts, the large ones would be difficult. And even sorry. Okay, so we're gonna move on to the next one. This one is gonna be addressed directly with the customer. It's a very specific question. What is the thickness that can be achieved? That depends on the coating, but in general, if it's more of a decorative application, it's going to be within half a micron. If it is a performance application, you're going to go into anything between 2-3 micron all the way to 5 and even further. But that depends on the application as well. Mind you, when you apply these coatings, you create stress to the coating. So there's a combination of how good adhesion is and what kind of stress you generate in the application itself. But in general terms, we can talk about 2 to 5 microns is pretty standard in the industry. You can go further depending on the coating and the application. What's the working temperature of PECVD? Actually is normally lower than the temperature that you would have in PVD. Anything between, below 200 C, you can create really good diamond-like carbon products or coatings. How does PECVD compare to PVD and CVD in terms of processing and performance in tool steel? Right. Again, taking PVD, let's say if you're using a sputtering process instead of cathodic arc, and I'm sorry I'm being specific about the process. Just a disclaimer here, we do have webinars that focus on the processes themselves. So at that distinction of what kind of PVD process you use would be, I would go in more detail in that case. But in the case we're talking about here, PVD and CVD. The PVD, if you do sputtering, you do have to go to a very high temperature to get the coating that you want. And then you have to watch what is the maximum temperature that your tool still can take. CVD is even, if it's thermal CVD, then you have to be even more careful. Thermal CVD normally is used more for carbide tools, for instance, not as much for tool steel. PECVD you can apply to both. Again, we're talking about diamond-like carbon in this case. What's the thickness that can be achieved? I think we talked about that. Is it possible with DC magnetron to have zircon nitride? Yes, you can. There's nothing that's going to prevent you from doing that. It's just that when you use your process, you probably have to input more energy into it. Cathodic arc, which is the other process that we use mostly for decorative applications, it by itself generates a lot of energy because it creates ions during the process. Magnetron has a very low ionization rate, and I'm sorry, I'm going to details of the process itself. So generally, you have to apply temperature to help generate the reaction that forms the compound that we're talking about in the case zirconium carbon nitride. So that's one of the limitations that you may have with these magnetron sputtering. Which of the coating you mentioned are possible? Most of them can be done with arc. So that's hold on, let me just get the quote. Yeah, mentioned possible with arc. So all the zirc coatings, every single coating that I showed in there can be done with arc. The DC magnetron sputtering, there's just a limitation that I was just talking about. If you do want to have a certain composition, you do have to use other artifacts, other parameters to create that. It's not as easy as you would do with arc. There are differences. Then you would say, why don't you just use arc all the time? There's pros and cons, like in everything else. Again, this is the type of stuff that we would answer doing an examination of the processes themselves. Next question is interested in chrome nitride. Does Vaportech provide service to apply this coating compliant? We don't typically do that. We do that. We only do coatings if that leads to a sale of an equipment. So it's just one of those things we're just trying to validate the process if someone is interested in buying a piece of equipment. How is outdoor 24/7 durability? Most of these coatings do have very good resistance. Some of them may be affected a little bit by UV, and in our case, I'm just saying that because we are extremely strict about, if we're talking about color, for instance, very strict about what kind of variation is acceptable, right? In general terms, for the general public, most people cannot tell the difference. In terms of the application, if you have a performance application, meaning if your question goes towards, is humidity going to affect, is going to corrode the coatings and so on and so forth, then it depends on the coating. Chrome nitride and zirconium-based coatings are extremely resistant to the environment. Next question, are there any coatings that match or come close to low coefficient of PTFE Teflon? Yeah, some of the DLC coatings do get close. Of course, the advantage of a DLC coating is much higher than the PTFE, the Teflon coatings, right? May not get to the same level of those, but it gets close with the additional advantage of mechanical properties that brings to that particular case. Can you produce multi-layers with arc PVD? Definitely. We do that on a regular basis. So it's just a question of adjusting parameters, adjusting gases, introducing certain steps during the process, so you can create multi-layers, and can go all the way from layers where you have a gradient, as well as you can actually form some sharper interfaces that in some cases, especially if you have an optical coating or something that you are trying to achieve a certain appearance, it's necessary. So the answer is yes. Is magnetron sputtering similar to PECVD? No. Magnetron sputtering, being a PVD process, uses a solid source to create part of the coating, right? Or the entirety of the coating. You can deposit a pure metal, or even in some cases, if you have radio frequency power supplies or different types of power supplies, you can create from a solid source that is an oxide, for instance. While in the PECVD process, you start your process just by putting gases inside the chamber, or vapors inside the chamber. What I mean by vapors, you can have a source that is a liquid at room temperature and pressure. And as you introduce that into a vacuum chamber, it becomes a vapor, and that then becomes part of the coating. Part of that vapor becomes part of the coating. So that's more or less how it works. And if not, what's the difference, and which one is better for performance in tool steel? That goes back to that question, right? What exactly is the application? If you're looking for, let's not talk about tool steel. If you just think about the application itself, if you have an application where most of the failure that you see on your tool is due to wear and sliding, you can go with DLC. If it is something that requires a harder coating, then you're going to go towards titanium base, or zirconium base, or chrome base. What's the competitive features of your cathodic arc? That's a great question. Cathodic arc is a much faster process. A deposition rate of cathodic arc is much higher than what you would have in a standard being the key word for sputtering processes, right? You do get a lot of material coming out of your target, which then becomes your coating. So that's more or less the advantage of cathodic arc with respect to sputtering. If you compare it to our specific process compared to other types of manufacturers that sell cathodic arc, we are very different in a sense that our target is a central target inside the chamber, in which case you have spraying, and that's not the right technical term, but it gives you a good idea, spraying material in all directions at the same time. So you have really good coverage. You can keep your parts away from that target. You don't have to be rotating inside and going close to those other type targets that people use on the side of the chamber. And temperature wise, you can control it better. So we deposit on, we can deposit on metals, we can deposit in zinc cast, brass cast, ABS plastic, and so on. What is the largest surface area that can be coated using PVD process? Well, that's just depending on the size of the chamber. And again, it's I think I addressed some of that at the beginning of the question and answer part of the presentation. Okay, Ozzy, I think we're getting to the end here. Do you want to come back in, or?
Yes. Sorry, it took me a moment last time and then you just carried on, didn't need me. Thank you everybody for coming. I have put some links and files in the webinar chat. You will also all be getting a link to the recording of this presentation. We appreciate your time as always, and look forward to seeing you at our next webinar.
Yeah, thank you so much. And if you have any additional questions, don't shy away. Just send them to VaporTech. It will make its way to someone that can help you with answering those questions. Thanks again for participating. Bye-bye.